Unit 8, Reading 3, Representing Change Using Energy Flow Diagrams. Why do we need to use energy flow diagrams? This reading describes the third tool we use to help represent energy flow diagrams. The use of flow diagrams will help us to be more quantitatively represent energy storage and transfer. Together with system schema, the energy flow diagram will help us represent how energy storage changes when energy is transferred within a system. Energy flow diagram will also be very useful to help us represent changes when energy transfers into or out of a system across the system boundary. What does an energy flow diagram look like? Here's an example of an energy bar chart. Important features on the energy flow diagram. Before making an energy flow diagram, be sure to define your system and make a system schema if needed. Remember, the system schema diagram identifies the objects that interact during the process or change. Next, an energy flow diagram will help us track changes in how the system stores and transfers energy during the process or change. Each bar or block in the initial graph or final graph of the energy flow diagram represents how the system is storing energy. The circle in the middle is used to represent the system. Also, the circle in the middle can be used to show energy flow. We can use quantified arrows like the bars on the bar chart that point into or out of the system to represent the amount of energy being transferred into or out of the system. If there are no transfers of energy into or out of the system, no arrow would point into or out of the system. This means that the system was chosen to include all relative objects, and the analysis is simplified. In this instance, the initial and final bar graphs must have equal number of blocks or bars described among the different modes of energy storage. Steps in constructing an energy flow diagram. Identify a system. Draw the system schema. Identify the initial energy storage modes and represent them with bars that depict relative amounts of energy in each storage mode. Identify the resulting final energy storage modes with final qualified bar graphs. Identify energy transfers. If an energy transfer occurs across the system boundary, represent this transfer with arrows pointing into or out of the system schema and to make the energy flow diagram. In summary, you will use energy flow diagrams to represent the initial and final energies, and the system schema and energy flow diagram to represent the intermediate processes. The difference in the initial and final energies is the system change in the energy, delta E. That triangle is a delta, Greek letter delta. Since delta E is equal to energy final minus energy initial. Thus, the system schema, energy pie charts, and energy flow diagram help us represent the conservation of energy. Scientists call the concept of energy conservation the first law of thermodynamics. The energy of a system stays the same unless energy is transferred into or out of the system. Examples of energy flow diagram. Example 1. A person pushes the box that was initially at rest across the floor. Friction exists. The system is the person, the earth, the box, and the surface. And you can see with the system schema how things are interacting. The system schema shows that energy cannot be transferred into or out of the system, since none of the object interactions across the system boundary. Therefore, the energy flow diagram, no energy transfers in or out of the system. Corresponding energy flow diagram. Initial diagram is 1, 2, 3, 4 pieces of energy chemical. And the final is 2 pieces energy kinetic and 2 pieces energy internal or EDIS. Analysis. The box has no initial stored energy, but the person does. Energy chemical. Energy is transferred from the person's stored energy chemical to other storage forms as the person pushes the box. Therefore, no transfer of energy occurs across the system boundaries. No energy is added to or removed from the system, and no arrow is shown in the energy flow diagram. At the final state, the energy is now stored partially as energy kinetic and partially as energy internal or dissipated, since the box and the surface have warmed during the process. Note that energy kinetic and energy internal add up to 4 blocks, which equals the initial 4 blocks of energy chemical in the agent with the conservation of energy. Example 2. A person pushes a box from a 0 position up a ramp to a stop. The system is the box, the surface, the ramp, and the earth. And in this case here, notice the person is not in the schema, in the system schema. The person is outside. So the system schema shows that the energy would be transferred into the system by the person or even out of the system to the person. So the corresponding energy flow diagram, in the beginning, there is no kinetic, no gravitational, no chemical, but 1, 2, 3, 4, 5 pieces of work energy are going into the system. Because the person is outside of the system, the energy has got to go into the system. And afterwards, there's no kinetic because the box is at rest, and there's 1, 2, 3, 4 pieces of energy gravitational and 1 piece of energy internal. Analysis. Assuming the box starts at 0 reference point and has no initial energy. Energy is transferred to the system via push provided by the person who is outside the system. We call this energy transfer by pushing working and give it the symbol W. If the person transfers 5 blocks worth of their energy chemical into the system by pushing, then working energy flow arrow is 5 blocks long. In the final state, the energy transferred into the system by working has been stored in the system of the gravitational field, energy gravity, and some has been dissipated due to friction, energy internal or energy dissipated. Note that the final energy of gravity and energy internal add up to 5 blocks. In agreement with the conservation of energy, the total energy in the universe did not change, even though the initial and final bar graphs do not match. The total number of blocks does. 5 blocks of work going into is equal to 4 blocks of energy gravity plus 1 block of energy internal. Example 3. A person lowers a box to the ground, and the system is the box and the earth, with the person being outside and the surface being outside of the system schema and the box and the earth on the inside. The system schema shows that energy can be transferred into the system by the person or the surface. Energy can also be transferred out of the system to the person or the surface. So the conservation of energy flow diagram, the initial is 1, 2, 3, 4 bits of gravitational energy. The final is nothing, with the understanding that 1, 2, 3, 4 pieces of work went out of the diagram. Analysis. Initially, the box has energy gravitational, E sub g, due to its position above the ground, which has been defined as the point where y is equal to 0. Afterwards, the box system has no energy. The box lies motionless on the ground. It might be tempting to say that energy E sub g was lost to energy internal However, it's difficult to imagine that the temperature of the box or the internal structures undergoing significant change in this process. Friction is minimal as the box is lowered, and we assume that it was lowered gently so it didn't slam into the ground. Therefore, the energy had to be transferred out of the system by the interactions of the box with the person who lowered the box to the ground by pulling or working. This is the case where the analysis is actually more complicated if the person is included in the system. That situation would be beyond the scope of this course. Example 4. Person pushes box that was initially at rest across a floor. Friction exists. In this case, the box and the surface are in the system, but the person and the Earth's field is outside of the system. The system schema shows that energy can be transferred into the system by the person or the Earth, or even out of the system to the person or the Earth. So the initial diagram has no energy with 4 pieces of work going into it and ending up with 2 energy kinetic and 2 energy internal or dissipated. Analysis. The box has no initial energy. Energy is transferred into the system, energy chemical, via the external pushing provided by the person. The working arrows is 4 blocks long. At the final stage, the energy transferred to the system is stored partially as kinetic energy and partially as dissipated internal energy, since the box and the surface was warmed during the process. Note that the energy kinetic and the energy internal adds up to 4 blocks in agreement with the conservation of energy.